Thank you all for joining us today. I'd like to start by acknowledging that I live and work within the traditional territories of the Kwanlin First Nation and the Town Council. For those of you who I haven't met yet, I'm Brianne Warner, the new Executive Director for the Yukon Chamber of Mines. And it is extremely important to the Chamber to ensure we continue to offer opportunities for industry to network and communicate their achievements and attract investments to our territory. With the decision being made primarily due to the imposed restrictions on gatherings, the idea of a Zoom speaker series was developed as a way to deliver on those commitments. If there's enough interest in the future, we'll continue to look at offering this type of Zoom series. If you are having any technical issues, please contact events@csrmanagement.ca. Also, please check out our silent auction, Northern Safety Network Yukon, along with Yukon Chamber of Mines and Yukon Reed Society, are once again working together to organize the fundraising auction to raise money for the Yukon Imagination Library and the Yukon Mines Legacy Foundation. All proceeds of the silent auction will go to the Yukon Imagination Library and the Yukon Mines Legacy Foundation. The auction will end on January 27th at 12 p.m. and the link will be posted in the chat. Thank you, Anne. Once again, we will have a Q&A session at the end of the talks. If you do have questions, please post them to the chat and our moderator will read the question and answer. Special thanks to our partners, BMC Minerals and Yukon government for putting on the speaker series, and our gold sponsors, Archer Cathro, Air North, Yukon's airline, Alcan Air, Cobalt Construction Inc., GDS Energy and Mining Inc., Newmont, NVD, Pelly Construction, Summit Cants, and Invest Yukon. With that, I will hand the mic to Carolyn Relf, Director for YGS, to make our first introduction for our speakers.
Thanks, Brianne, and good morning, everybody. Welcome to session number 2 of the Geoscience Speaker Series. This morning's session is going to focus on the Keno and Beaver River areas of Yukon. There are a number of silver and lead zinc projects underway there, and we'll hear a bit about regional geology and a couple of the projects that are underway. Our speakers are streaming from a number of different locations this morning, including Whitehorse, which, as Brianne said, is on the traditional territory of the Kwanlin First Nation and the Town Council. For folks who are watching, as Brianne noted, please put your questions in the Q&A and we'll get to them at the end after all 3 speakers have presented. And for folks who missed Tuesday morning's session, those presentations are going to be streamed through Geoscience, yukongeoscience.ca through the chamber. So without further ado, I'll introduce our first speaker. Tyler Ambrose is with the Yukon Geological Survey. He's been mapping for the last 3 years in the North Rackla area, and he's going to present an update on that geology this morning. Thanks. Go ahead, Tyler.
Good morning. As Carolyn mentioned, I've been working for the past 3 summers in the Rackla River area. This is a photo of one of our camps, and I'm going to be talking about the rocks and provide some updates on the mapping based on these three field seasons. So this is a terrain map of the Yukon. The field area is located here. It's east of the Tintina Trench, and for reference, Mayo is right here. So this area is located at the southeast margin of the Yukon stable block, which is an area of a region of relatively thick lithosphere. On the right here, you can see this aeromagnetic map. It's got a distinct magnetic anomaly here. And in the Paleozoic, the sedimentological expression of the Yukon stable block was the Ogilvy platform here, shown in this pale blue. And to the south, you go into the Selwyn Basin, where the lithosphere is thinner. In the Precambrian, the effect of the Yukon stable block and the history of the Yukon stable block is less certain. So this is a map showing the Devonian and older rocks in the Northern Cordillera. Again, for reference here, here's Mayo. And the oldest rocks exposed in the Cordillera, that's Pinguicula and Mordecai supergroup, shown in brown and orange. And they outcrop in a series of inliers, the Coal Creek inlier, the Heart River inlier, and the Warnicki inlier. On the bottom here is a more detailed view of this box up here, showing the Heart River and the Warnicki inlier. And the map area is located in this box here. So the area contains several notable mineral occurrences, including the Val and Beaver, or the Rusty Mountain area, and the North Rackla silver, lead, zinc occurrences. These red boxes here are outlining previously mapped 50,000 scale sheets. So just to the west of my map area, Charlie Roots mapped and had a map released in 1990. To the south, the YGS has a compilation of several 50,000 scale sheets in the Rackla trend here. And Stu Blesson in the 70s had some compilation of 6 maps, 6 50,000 scale maps here. And just wanted to mention to the north here, the northern margin of the Warnicki inlier, Derek Thorkelson's maps and the same rocks, and Grant Abbott's rocks in the Heart River inlier here provide a foundation and much of the knowledge of these rocks, and allowed me to build up to that. But the area that I've mapped was last mapped at the 250,000 scale, also by Stu Blesson. So he had a bunch of maps released in 1974. So 5 250,000 sheets and 6 50,000 scale sheets. So I'm building off that. And to give you an example of the vintage of mapping, this is what it looks like here. So many of the units that are now common and used today were unknown back then. And yeah, so trying to take this and push it forward with the new understanding of the stratigraphy that's been gained over the last 50 years. So the result, this is the result of the mapping. This is my map here on the right, and this is the new stratigraphy for the area. So what I'm going to do now is go through the stratigraphy and the map and build up the units, and then present what I think is going on here. So this is the oldest unit in the area is the Gillespie Lake group, and shown in blue on the left here on the map is the typical Gillespie Lake group. It's orange, red, brown, gray weathering. Well-bedded dolostone. It's locally stromatolitic, commonly microbially laminated. Within the Gillespie Lake group, you also get these brown polygons here, which are siliciclastic intervals. And this is an example showing in the background here, the typical cliff-forming dolostone of the Gillespie Lake group. And as you come down here, you get into this recessive strata here, and you've got a mixture of Dolo mudstone, silty Dolo mudstone, all the way up to siliciclastic rocks here, which is what the photo is taken on in gray here. And last year, this is a photo from the previous year and from my second year out there, and I interpreted this slightly differently, well, completely differently, I should say. So here's the typical Gillespie Lake group, and you go up section into this recessive mixed carbonate siliciclastic interval, and then you're up into just straight siliciclastic rocks. And I interpreted these siliciclastic rocks as being the quartet group, and this as being the base of the Gillespie Lake group, which necessitated thrusts. So I no longer think that is the case, and I think this is more likely reflecting just lithologic variation within the Gillespie Lake group. So the Gillespie Lake group is intruded by Heart River sills on the strat column shown here, and on the left in purple as well. And so these are mafic intrusions. Quartz is present commonly as a diorite to a gabbro. They can be quite thick, up to 250 meters, and they're non-magnetic, and I'll come back to that in a minute here. So the 2 main points I want to hit are that it preferentially intrudes these siliciclastic intervals within the Gillespie Lake group, in this area at least, and I think to the west as well, where Charlie mapped. And the other point to make here is that it does not intrude the Pinguicula group. So if you have Heart River intrusions, you have to be in the Warnicki supergroup. You are not in the Pinguicula group, and that's been something that flopped back and forth, but now it's fairly clear that that is the case. Here's a photo of it, Heart River sill shown here, and gray here, intruding one of these siliciclastic intervals. And up close, it often weathers this orangey to pinkish color. Okay, so the Gillespie Lake group and the Heart River sills are overlain by the Pinguicula group, which includes carbonate and siliciclastic strata. They're not known now, or they've been formalized as the Mount Longerville, the Pass Mountain, and the Rubber Creek Formation, but these were previously known as the Pinguicula A, B, and C, for those who are more familiar with that terminology. And as we move from the northwest here in these older Gillespie Lake group rocks, we're coming southeast as we're moving out of the inlier into younger strata. So this is a shot of the unconformity, placing the base of the Pinguicula group on top of the Gillespie Lake group. They can be quite difficult to distinguish, where you've got the siliciclastic rocks, fine-grained siliciclastic rocks of Mount Longerville over siliciclastic intervals of the Gillespie Lake group. Most of the Gillespie Lake group is a fairly monotonous succession of green, gray, and black weathering siltstones. But there's an important marker horizon right at the base, which is a polymictic conglomerate shown here. And so this photo is taken of a rock just at the base here. So where that is identified, you know you're at the base of Mount Longerville Formation. And this is about a billion or 1.1 billion years old, the Mount Longerville Formation. So the siliciclastic strata of the Mount Longerville Formation gradationally pass up section into a carbonate package of the Pass Mountain Formation, and another carbonate package, the Rebel Creek Formation here. Pass Mountain Formation is a dolomitic limestone. It weathers this kind of very bright, spectacular orange, and where it's less dolomitic and just more more pure limestone, it's gray here. You kind of get this feathery texture in here, blubby, and there's commonly cross stratification in these lenses here. Not in these photos, but often or in places it can be difficult to distinguish from the Gillespie Lake group, and it has been by myself and by others been misinterpreted or miscorrelated with the Gillespie Lake group in places. So the Pass Mountains overlain by the Rebel Creek Formation, Ping C. This is the uppermost unit of the Pinguicula group, and it's this beautiful pinstripe laminated dolostone, and you often get brecciation, and associated with that brecciation you get these zebra textures that are developed where you've got replacement of the dolomite with this coarse crystalline orange, commonly orange to pinkish weathering, coarsely crystalline dolomite. So continuing to the southeast as we move out of the core of the inlier into this younger stratigraphy, and overlying the Pinguicula group is the Hematite Creek group. This Hematite Creek group was split out of the Pinguicula group about 20 years ago, but originally it was a continuation of the Pinguicula, so from A, B, C up, and then Hematite Creek was D, E, F. So I haven't divided the Hematite Creek group in this area based on the limited exposure, but yeah, it's closely related to the Pinguicula group. The Hematite Creek group, again, is a mixed siliciclastic and carbonate package. There's an incredible variety of facies that contained within this group. These are carbonates here, carbonate clast conglomerate. You've got an abundance of sedimentary structures here. You've got some cross lamination, some desiccation cracks, and here's one of the rare stromatolitic dolostones. But I guess a ringer for knowing that you're in the Hematite Creek group is this gray weathering arcosic to quartz sandstone that it occurs as thick successions, hundreds of meters thick, all the way down to thin interbeds within carbonate and other siliciclastic strata. This is a photo in the back here. We've got Pinguicula B, or Pass Mountain, all the way up here through Pinguicula C, and this is overlain by the Hematite Creek group here, interbedded dark shales and dolomitic sandstones, and here in orange. And again, here at the base is this light gray weathering sandstone of the Hematite Creek group. And in the background here, you can see the Mount Longerville. So you can see Pinguicula A, B, C into Hematite Creek. So it's a spectacular spot area to walk through the whole succession. So overlying the Hematite Creek group is the Windermere supergroup. I'm only gonna, so that includes the Mount Harper, Rapitan, Hay Creek, and Rackla groups. These are all exposed in the area, and you notice the map didn't change too much here. The exposure is very limited to the south here of most of these units, southwest. And the only units that I saw this last year and the year before were the Rapitan group and the Callison Lake formation here. And you can see that their exposure is more extensive here, this green and maroon here coming through here. So the Callison Lake formation is a resistant Great Dolostone, and characteristic of it is this irregular chert layering here. That's discontinuous and can form quite some interesting shapes. And overlying the Callison, unconformably overlying the Callison, is an orange and maroon weathering dimectite to conglomerate, shown here with a huge range in class size, very poorly sorted. And interbedded with this, and as well as forming larger sections, you get siltstone, shale, and sandstones. So the Hematite Creek group, at least, and potentially younger, maybe the Rapitan group, is intruded by the dike swarm. And so the dike swarm consists of these mafic 2 to 3 meter thick, east-west striking vertical dikes. And they can resemble the Hart River sills, but there are some striking differences. So in addition to the consistent orientation, they contain minor olivine, and they're quite magnetic. So they can be distinguished in the field from Hart River by their magnetism, and in mag surveys they can be distinguished as well. So yeah, there's one spot where I've seen it intrude the Rapitan group. There's a dike that has a similar orientation that may be related, but it certainly intrudes the Hematite Creek group. So these are undated, yeah. So this is what they look like. This is just east of the North Rackla camp. So this magnetic dike here is the one that cuts right across North Rackla, the North Rackla property. This is a Gillespie Lake group. This is one of the more recessive intervals within the Gillespie Lake group, up to the more resistant cliff forming dolostone. Again, here on the top right is Gillespie Lake group. And these dikes cut this fold here, and I'll come back to that in a few slides. And here's the dike cutting the Pinguicula group. And these are really obvious and conspicuous in Gillespie Lake group, this in the orange dolostones, and in the Pinguicula group, but they can be more difficult to identify within the siliciclastic rocks of Gillespie Lake and Pinguicula. So they're geochemically distinct from the Hart River as well. They plot an alkali basalt field as opposed to Hart River, which falls in the basalt field on this modified Pierce, modified Floyd and Winchester diagram. And they're enriched, and just so in the bottom here, the east-west dikes are shown in red. And you can see they're more enriched in heavy rare earth elements, similar to Ocean Island basalt, relative to the more depleted Hart River sills, which are shown as the black lines here, that are similar to Morbs. So overlying, unconformably overlying the strata over the older strata is the Bubette formation, and I'm not going to talk too much about this because I didn't see much of it this year. But it's this monotonous succession of gray dolostone forms. It's quite thick and it's locally fossiliferous. And you can see a very gentle fold in it here. So what does this all add up to? So on the left here is the existing compilation map, and this is the updated geology that I've been working on the last few years. So there's a few points I want to point out here. Starting in the top left here, one is this, in the compilation map, this is, and previous people have interpreted this as being, including myself, have interpreted these siliciclastic intervals as being the quartet. These I don't believe exist anymore. This is just a siliciclastic package within the Gillespie Lake group. Second, there's this large area of Windermere on the pre-existing map, and again, that no longer, it's much more limited, the exposure of the Windermere supergroup rocks, and a lot of that is actually Pinguicula and and Hematite Creek group. And finally, the existence of this dike swarm here. It was some of these dikes that do occur on the original mapping by Stu Blesson. However, they were interpreted to be the same as the Heart River sills, and both of them were interpreted are thought to be Cretaceous. So we know now no longer that is the case. So the map area, switching to structure here, can be divided into three domains: a northwest, a northeast, and a southern domain. So this is based on the orientation, compilation of bedding, axial plane, foliation, fold axes, and intersection lineations. You can see that the orientation of structures in each of these domains is distinct. So the northwest domain predominantly consists of older rocks, but it's important to note that it does include structures, or the structures of the northwest domain do occur within Pinguicula group rocks as well. So this is easiest to interpret from a regional scale. So the map area here, located at the southeast margin of the Wernickean Lyre, which itself is at the southeast extent of the Yukon stable block, and it's squeezed between two structural domains: the Richardson Fault Array here to the northeast, and the Dawson and Kathleen Lakes faults to the south. So these domains on the map here, the northeast and the southern domains, appear to be related to these structures. And so these are younger Mesozoic, or more likely Cenozoic structures. And the Richardson Fault Array has modern seismicity, so the structures here are parallel with these younger structures. So that leaves the northwest domain. So what can we say about the northwest domains? The structures affect the 1.38 billion-year-old Heart River sills, as well as the Hematite Creek group. So that means that deformation, so this has to preserve a phase of deformation that's younger than 1 billion years old. But the structures, they're older than 780, so they're younger, so they're older than the Callison Lake group. So that brackets it between 1 billion and 780 million years. And just to point out, so that means that this is not related to the Rackla orogeny, which is 1.6 billion years old. So this is a younger phase of deformation. So switching to the mineral occurrences here in the area. So the revised stratigraphy allows me to say something about the mineralization in the area. So you've got these carbonate hosted ones shown in red. So in the map area, this includes the North Rackla and the Beaver occurrences. And these occur in carbonate rocks of the Gillespie Lake group, but they're adjacent to these siliciclastic intervals in both cases, whether the North Rackla and the Beaver. So that suggests that there's perhaps a structural, the competency contrast between the siliciclastic and carbonate rocks was favorable for mineralization and developing the plumbing. The Val occurrence just to the south of Beaver is hosted in the Rebel Creek formation. And then these are more regional outside of the mapping area, but the point is to show that you've got a large time span of mineralization in this area and within these rocks. So yeah, this is the final slide here, and I'm just going to provide a brief summary of everything, a synthesis. So the area exposes Paleoproterozoic to Cambrian to Devonian stratigraphy. There's major unconformities that separate these units. The Gillespie Lake group is intruded by the Heart River sills, and then unconformity overlined by the Pinguicula. These magnetic east-west trending, this east-west trending dike swarm cuts rocks as young, at least as young as the Hematite Creek group, and possibly much younger. There's two phases of deformation. There's Neoproterozoic structures preserved in the northwest part of the map area. So it's bracketed to about right here in the stratigraphy, so beneath the Callison, but younger than the Hematite Creek group. And then there's these Mesozoic to Cenozoic structures related to the Richardson Fault Array and the Kathleen Lakes Fault in the south and the northeast part of the map area. And then throughout the stratigraphy, there's mineralization, different types of mineralization that occurs at different stratigraphic levels and in different units. So that's all I've got. So I'll leave it with there. And if you have any more questions, feel free to send me an email. And there'll be more details coming up in my YAG and an open file map that will be coming out shortly.
Thanks very much, Tyler. As I mentioned, we're going to hold questions, but just to put in a further plug for the YEG that Tyler mentioned, we will be releasing our annual Yukon Exploration and Geology volumes at the Roundup this year. We have a virtual booth, so you can download them there, or you can grab them off our website. And it'll include the overviews, the presentations you saw yesterday, and a number of other YGS talks that are upcoming. Our next speaker is Greg Lynch. He's a consulting geologist with Metallic Minerals. He's been working in the Keno Silver Project. And the title of his talk, hang on a sec, Imbricate thrusting and aplite intrusions within the Tombstone Strain Zone in the East Keno Mining District with enhanced plumbing for hydrothermal mineralization, implications for silver exploration. So over to you, Greg.
Okay, thanks for tuning in, everyone. And thanks to the Chamber of Mine for putting on this series. Very helpful after all the challenges. And basically, I'm going to be talking about Keno Hill Mining District. And it's actually a return to the district for me. I was able to get out there with Metallic last summer. And I was working with Taylor Haid and Greg Johnson, co-authors. I spent approximately 8 weeks in the field. So I was working there in the 1980s, and I completed a thesis in the region focused mostly on the mineralogy and geochemical aspects of some of the veins. I subsequently went to work for the Geological Survey for 10 years and learned quite a bit about structural geology. And then I worked in the oil and gas sector in the Canadian Rockies foothills, where there are imbricate thrust systems. And some of the principles of that, I think, do apply here to the Keno district. So, and they have implications for the mineralization, which we're seeing. So I'm going to get into that. Basically, we're in central Yukon. You can see the location map here. Keno is well known, of course. They've been mining there for off and on for over 100 years, since the late 1800s. Basically, the town of Mayo is right here. We're just a 40-minute drive north of Mayo. Dawson's over here, of course, on the other side of the Tintina Fault, completely different domain. The Keno Hill quartzite is kind of shown in this mauve color here from the website, YGS's website. I took this screenshot. It's Mississippian in age. And it strikes for approximately 250 kilometers east-west. There's lots of mining interest in the region. You can see there's Eagle Gold here, Brewery Creek, and the Tombstone Plutonic Suite intrudes these rocks. The quartzite everywhere along here is actually sitting in the footwall of the large Robert Service thrust. So part of the theme is that the Robert Service thrust doesn't act alone as a one-off. There's actually some sister faults in the footwall of this through the mining district. And we'll do a quick comparison over here with Tombstone, where they've been mapped out quite extensively. The other thing we're seeing too is that the Road River Formation, the Platy Limestone and the Ribbon Shirts, we're finding these rocks in the hanging wall of the Keno Hill district. So we'd be proposing some sort of revisit of the stratigraphic breakdown of this part of the area. So as you can see at the west end of the Keno Hill here in this mauve with MKHQ, Thompson and Mustard and Roots, they mapped extensive series of imbricate thrust systems through the Keno Hill quartzite, resulting in a much thicker interval. Thrust over the Bug Creek Jurassic, so it's post-Jurassic in age, and pre-Tombstone, so mid-Cretaceous. So that brackets the age. And here the greenstone is Triassic diorite sills, which have been thrust. Almost all of them have been transported extensively. So we could come around the bend all the way to the east, and in the Keno district, none of the current or recent mappings and historic maps through the area have picked up that theme in this area. And you can see the stratigraphic repetitions, partly due to folding, but we believe also they are rooted above important thrust faults, which haven't necessarily been recognized. So look at a couple cross sections right here through Keno Hill itself proper, and a bigger section here as well in the district. And that would look like this. So in a way, this is McTaggart's section through into Monument Hill, adjacent Keno Hill and Hope Creek. And in 1960, he did his work in the 1950s. He made a great map, and he proposed thrusts. You can see I've highlighted them in red here, and imbrication just refers to the repetition or stacking of the same unit over itself several times. And here the thrust runs along bedding. And if you didn't recognize the thrust, you would overstate the thickness of the Keno Hill quartzite in this area. And you can see fault propagation folds, which have been broken through by the thrusts. And these folds are widely recognized. So in a sense, for me, it's really a back to the future situation with, I think McTaggart had it largely right. Soon after, in 1965, Boyle published an excellent map through the area and did all his classic economic geology work on the district. But he didn't incorporate the theme, the thrusting theme. And things kind of stayed in that way since then. And so this feature that McTaggart was seeing was kind of left aside. And I think it's worth considering bringing it back into the area, considering this is sandwiched between the overlying Robert Service thrust and the footwall Tombstone de Colma. We think that we can actually incorporate evidence for some of these thrusts actually through the district here. So that would be a version of the revision we're proposing. And in structural geology, we often say that the small scale reflects the large scale. So this is a ribbon banded chert in the hanging wall of the Keno Hill quartzite, which we would correlate to the Road River group or division to Devonian aged equivalent rocks, at least descriptively. We don't have quantitative age dates on this yet. It's a matter of correlation, and our call would push it down in the stratigraphy as opposed to up above Keno Hill. And you can see the strong north verging folds. This is in the hanging wall of the sourdough thrust. It's called the sourdough member. And again, here, the very strong, tight to nearly isoclinal folds. And the stacking of the laminae here, basically thickening the unit occurs above basically a flat sliding surface. And so this style of folding is recognized often, but nobody's gone out and put these lines on the map. So this is what our updated map looks like. And of course, Murphy and Roots had mapped quite a bit in this area, and Alexco, in collaboration with YGS, have put out a nice map in this area here recently as well. And in the 8 weeks I was up, we were spending time up through this area here and further to the east and elsewhere, and up onto Sourdough Hill. So we were basically looking at stuff surrounding metallics block in these regions. And basically, you can see at a map scale the repetition of the Keno Hill quartzite, partly a fold feature, but we think also carried on thrusts. And the thrust, basically, the line of the thrust is where the older urn group, which is shown in gray here, basically is carried up and sits on top of Keno Hill quartzite. And when you walk these lines, you can actually see fairly thick and penetrative shear zones, which we can relate to transport and deformation. And that comes back 3 times here. If true, the reassignment to Road River also puts older rocks here on top of Keno Hill quartzite, which all of this is dipping moderately to the south. And the greenstone belt, the Triassic rocks here, are completely absent across this line. And basically, these rocks here might actually be have been relatively far traveled because they were out of reach of this Triassic intrusive event. Cambrian Proterozoic sits back here in the Highland group. Okay, so just to place ourselves, we're going to look across the valley here. So we'll stand on Caribou Hill and look across Silver Basin to this site here. And so we'll look a little closer as to what the proposed thrusts look like right here. And so we're standing on some high ground right here above a cliff on Caribou Hill, looking to the west. And basically the silver basin occurrences are occurring here, the traditional veins. This is close to being an extension, an extrapolation of the main vein at Keno. We have typical galena, sphalerite, siderite mineralization along these. And it's overprinted by quartz and epithermal mineralization where these intersect the thrust faults. This is a big panel of blocky Keno Hill quartzite. And above that, at this contact, we have highly sheared urn group in outcrop here, which we'll be looking at. And the other fascinating thing too is that the aplites, there's tombstone aged aplites, which we've dated, and I'll talk about that, which run right along the thrust for 12 kilometers. And it seems that this thrust, if that's what it is actually controlling the intrusion of the aplite as well. And the stratigraphy repeats itself. You go down here. This is what would be the normal stratigraphic contact into the urn group. These are metavolcanic chlorite muscovite schist. And basically the next contact down where this is popped up over the Keno Hill occurs here. So basically you'd have a series of 2 imbricate thrusts right in this field of view. And so let's just look at this here. So basically, this is bona fide shear zone rock right here. You can see my mouse, and it's a muscovite chlorite quartz vein Ogden schist, and it's from the volcaniclastic rocks of the Devonian urn group, and it can be tens of meters thick, and or more actually, and maps along strike for several kilometers. When you're in this rock, you know you are in the thrust zone. And the thin line on the map of the thrust proper is the actual contact between this unit and the underlying Keno Hill quartzite, or essentially the top of the Keno Hill quartzite is where you would draw the line of the thrust. You can see these large, what's very typical, it's a very knobby rock whereby there's, it's just rife with quartz vein Ogden, which are active asymmetric rigid inclusions, which actually give you a sense of shear with tops to the north asymmetry, caught up in CNS type structures, typical of shear zones. And the outcrops are very knobby, very distinct. This rock is quite mappable and occurs from here. We can carry it up all the way over onto McFall Ridge, several kilometers away. And again, you can see the asymmetric Ogden schist basically with an interpretation of the sense of shear sketched on here. And here it is, an outcrop. It's very bumpy with all of these quartz nodules. It's quite a striking rock. And in the footwall, relatively less strained or deformed is intact blocky Keno Hill quartzite, which sits passively below this overthrust unit. So from Sourdough Hill going northeast through Caribou, this is what a cross section would look like. The units dip moderately, approximately 30 degrees to the south. And you can see here as you walk the surface and map these things, the repetition several times of the Keno Hill quartzite. And of course, we have this intense folding we talk about. But we have basically where you were just standing and looking across the valley to here, that's basically the view with the mappable shear zone occurring above this. And this is the urn group transported up on top of the Keno Hill quartzite with the repetition of the quartzite here again. And I've drawn on here some of the major known mines and past producers. And they basically dip moderately to the southwest, and they are largely stratabound for the most part, or they're much better developed in the quartzite. So you can see these red streaks would represent the mines. The greenstones are also excellent hosts for these main stage veins, and they post-date and cross-cut the thrusting. So they're younger than the thrusting. And they're also younger than the aplite, which we've dated here, in this case from surface, as 93 million years old. Another twist is in the paragenesis, and I outlined this in my thesis in the 80s, and we're seeing it still, is the occurrence of late overprinting epithermal phases. And these are preferentially at the intersection of these thrusts and the main phase mineralization. And we have a lot of occurrences around the district whereby they occur independently of the main stages. And they provide independent target to go after. And the type deposit, economic past producer would be Silver King, which is entirely epithermal in nature and has none of the traditional galena siderite assemblage in it. And so basically you can see here, just to refresh everyone's memory about the Keno Hill ore, is this siderite with galena, and the galena has inclusions of tetrahedrite, which is basically giving this the high silver values. And paragenetically, in all the main veins, you always see this early quartz phase as a stockwork. And this quartz is high temperature with carbon dioxide rich, very high pressure fluid. And is buffered to carbon dioxide rich because of the presence of graphite, which buffers the system. When the faults move, it cracks off the pressure, and the pressure leaks, and the CO2 escapes. So the pH goes up and the carbonates are happy. They fall out with the sulfides. So it's kind of a fault valve model for mineralization rooted in the graphite buffer. Late stage quartz is seen here. This is the epithermal phase, and this quartz is completely different. It's low pressure, relatively low temperature quartz, euhedral, and it's late and fills bugs and cements late breccias that we see in the faults. So a view to the epithermal phase, you can see a toothy little euhedral quartz here, late quartz filling the vug and crack with the ribs of quartz crystals. And you can see the native silver here from the epithermal assemblage. You can see the fracture coated with parargyrite, ruby silver, and acanthite. This is from Silver King. You can see the speckled pyrite with fine-grained sulfur salts, wire native silver. And so basically what remains of this in the district is this thin lattice of late quartz. And we're starting to see this much more widespread than previously thought. We used to think it was strictly a West End Husky Rays 224 and Silver King at the West End, but we're seeing this quartz now all over the district, and including east of Keno Hill. And this draws your eye to the epithermal event as being a potential exploration target in its own right. So the conventional galena siderite assemblage is shown here. This is from 1986. This is a part of the Hector Calumet system, southeast dipping fault with some remnant ore. The galena is ribbon banded, so twin galena, it's sheared along the fault. And so it's the fault movement was actually continuing after the mineralization carried through it, which results in late brecciation and keeps some of the space open for the late epithermal phase. And you can see the siderites brecciated here, and this is still galena and tetrahedrite, so it's still part of the main phase. But I'm showing some textures which give evidence of active faulting during and after mineralization. And this is from the central area here. You can see Boyle's map. Okay, so basically, I just want to see where this is going. Oh yeah, we're going to look at the sourdough thrust here, and it's exposed along here and often Silver King area as well. And there's a strong geophysical anomaly which helps continue the thrust through here. And then the sharp line, like I was saying, where the greenstones stop, you go off into the sourdough member. And the markers, which are diagnostic, are these platy limestones, which you don't see in the Keno Hill quartzite. And the ribbon shirt is found down in this area. So the greenstones I talked about, they're quite thick sills, and they're really widespread, Triassic in age. You can see the feldspars here and the chlorite and actinolite. So this is in composition dioritic. They were very competent, tough rock. And so if we go to that area at the top of the Keno Hill quartz site, this is the Keno Hill quartz site. This is metallics Mabron vein occurrence, and there's some remnant ore right here. But you can see the big blocky nature of the quartz site, and it's tucked immediately beneath, up above here, the contact with the overlying sourdough member, where a lot of the deposits are focused along that contact. And above we have in the sourdough member this platy gray limestone, which you only see up in that part of the map belt. And I showed an earlier shot of the ribbon chert, and you can see the milky white, thin laminated to thin bedded chert beds with some resting dolomitic laminae incorporated in there. So descriptively, these actually are a pretty good match for some road river. But, you know, of course, additional work needs to be done to confirm this. It's just a field call. But the rocks are so different up here that I hesitate to associate them with Keno Hill units. And I talked about the asymmetric north verging folds in the ribbon chert. We also have quartz vein Ogden schist with these rolled up kind of snowball textures indicating tops to the north shear. You can see a milky white, very fine grained cherty horizon here with the bed pinched off as a boudin, and then the long axis rolled up on end. So again, indicating some sort of vorticity or simple shear in the component deformation of these rocks. And we also have these back tilted dominoes. You can see the bed here is offset and tilted over and bound by this overriding through going shear band. So these are typical of shear zones in the general shear category. So you can walk this thing out for tens of kilometers along strike. And if we get all the way around to the Silver King mine near Galena Creek, you can see here a bed of thinly bedded sandstone with graphitic schist in the sourdough member above the Keno Hill quartz site. And you can see this typical imbricate stacking of the bed, so thickening of the bed here. And again, the small scale is a reflection of the large scale. And they were driving an adit along this thing. So presumably they were following a mineral seam along the thrust zone. Below this, a few meters away in the footwall, is the blocky Keno Hill quartzite shown here. So this rock is being tectonically thrust and transported over top of this rock. And the trace of the thrust is the top of the Keno Hill quartzite. So age dating, I've picked up the YGS map from the website because they had posted on there some of the regional geochron data. So Keno Hill quartzites shown in purple mauve here, just to orient yourself. Keno City's there. And the large root granite, or what's also known as the Mail Lake Pluton, depending on the reports you're reading, is 92 to 94 million years old. We've added some new dates. We have two back now from the dike I was talking about at Silver Basin. Here, and it's 94. We have a sample from occurrence at Cobalt, 93. These are the same age within error margin. And there's from 10 or 12 years ago, a couple aplite dikes sampled here with the same age. So these are tombstone ages. And this is the first age of an aplite dike in the Keno Hill quartzite proper on Keno Hill. So we thought that was worth sampling. The aplites look like this, so they're concordant to schistosity. You saw from Silver Basin the trace of it in a cliffside view, and you can see the contact here with the metasediment, and this buff-colored unit here is fine-grained quartz porphyry, sometimes quartz feldspar porphyry, granitic aplite. Other views of the aplite, you can see the geologist here for scale. And this is an intrusion of an aplite, again, along schistosity. This one's approximately 8 meters thick. So it is concordant, but if you really peer in at the contact, at least in this exposure, you do find the aplite with small truncations of the S1 schistosity. So it is cross-cutting to some degree, but structurally controlled to the delamination of the schist fabric. Here's a smaller one, a long schistosity. You can see the trend of the schistosity. This is graphitic schist from the Ern group, and this one is approximately hammer width. And they also intrude the greenstone. So the greenstone is more massive. Some of its dioritic aspect is preserved. Very competent rock. And when the aplites come into the greenstone, they're not necessarily oriented along the same direction as the regional schistosity. So they have their own fracture system. So this is Boyle's map. I just go back to this one because Boyle had traced out this aplite quite well in his map. So I thought I would tap into his version of this. And the sample we collected is right here at an occurrence that's known as Faith, and that's 94. And this strip here, there's a few gaps in it, but I mean, you can correlate it along strike for 12 kilometers. That's a long strip of aplite. And again, from Caribou, we had looked over to Silver Basin, and the contact between the muscovite, chlorite, quartz ogden schist is right here, the shear zone. And this is older rock sitting, dipping 30 degrees south above the younger Keno Hill quartzite. And the aplite runs along the thrust. So there seems to be some symbiotic relationship between Tombstone age aplite intrusions and these thrust faults. There's another large one here. So here we have Ern group on top of Ern group. So we can't be sure that we're actually on a thrust, but it's a candidate for an in situ thrust. And then there's potentially another one down here where the outcrop starts to get lost. And overprinting this as a later phase is the main stage faults, which have the galena siderite form of mineralization. And we like where they actually intersect the thrust faults. So the aplites are shown in red here. These are poles to plains and the S1 fabric. So they both dip gently to the south. This is the direction of the trace of the major thrusts as well. And these are oblique to, these are poles to main stage mineralized faults. And these are from all the producing mines in the district. They've been compiled here. And they define a plane that looks like this, on average, dipping to the southeast at approximately 60 degrees, with some markers suggesting sinistral offset to a large degree along these. And they're just a bit younger than the aplite system and the thrust system. And this is a cross-section schematic. So this is in cross-section view, just to say that in thrust systems, the least resistance is vertically. So the rocks pop up during thrusting, and you can create low angle openings, which allow for things like aplite to come in there and potentially hydrothermal circulation. So if you, it's accentuated by this flat and ramp geometry of thrust systems. So this again is a cross section through a thrust. And these flattened ramps are the equivalent of, say, dilational bends, which you can often think of in strike slip systems at the surface when you're looking down on them. But if you're looking in profile and thrust systems, the openings actually occur along the flats. So when this rock is moving up, it's peeling off the flat beneath it where you get the opening. So here's a cross section, and you can see the flat which runs along bedding, kind of like McTaggart was drawing. And then when they cut up section, when this rock starts to move upwards, the delamination occurs along the flat here, and you allow for opening and your aplites start coming in there. And hydrothermal activity. So I just want to see where I'm at here. Okay, so a couple more slides just to show the east end of the district here. We have more of this thrusting mapped out, and we can carry the Silver Basin system off over here into what we call zone 2 and just above Fox, as well as Keno Hill repeats through this area. So this part of the map is actually entirely new interpretation. So this doesn't look like the maps that you might be used to getting your hands on. The root Pluton is here, and the metamorphic aureole is shown here as this pink, which is another story for another day. In that cross section, you can see the imbricate repetitions of Keno Hill quartzite and potentially some thickening of this quartzite. We have aplite bodies, 3 new bodies mapped here, here, and here. And metallics close grid sampling across the district over here has shown a whopping 3 kilometer soil anomaly across this area, which is why we're interested in unraveling what's going on there. And you know, it ranges across this entire area continuously between 6 to 100 grams per ton silver equivalent in soils. It's quite a phenomenal anomaly. So basically, we have some sulfide lenses through here. We're unraveling the complex mineralogy of that. There's some clear epithermal mineralization across this overthrust of greenstone, kind of in the style of what you saw at Tombstone in the second slide. Basically, the Imbricate thrust system is continuous here, and we continue exploration north of Keno Hill into the Urn group. So if you go to the top of the mountain, you can see these strong north verging overturned parasitic folds sitting up above the Keno Hill quartzite, again arguing for that north transport. The aplites look like this, porphyritic feldspar quartz porphyry. And at this site here, the thrust features greenstone, and it's massive and not highly strained. The thin edge of the thrust is here with a thick shear zone beneath it, which is also part of fault rock and damage zone, accommodating the overthrust with vuggy late quartz fills and some fine epithermal minerals in there. And that same greenstone is shown here. You can see some of the quartz veins running along it here and here. The thrust fault, the thin edge of the thrust is here, but really it's a shear zone. And the damage zone through here has distributed mineralization across this contact. And you can see some of it here. There's fine quartz, pyrite, and sulfur salts. And you can actually see them with binocular microscope and in hand sample. And a couple RC wells going through this. We have 30 meters of anomalous silver values across this contact, and a couple of adjacent wells, 20 meters over here. And so it does appear that, you know, the thrust in this case is controlling some of the mineralization. So the aplites have a pretty key role in this, not that they're contributing anything to the mineralization because they're still somewhat older. But what they do is they create leaching in the quartzite. So quartz is very temperature sensitive. If you add a big temperature spike, such as an aplite along a thrust, along a quartzite, the solubility of quartz goes way, way up. And any water sitting there in situ or along that fault being heated will simply start to dissolve a lot more quartz. And so you get a remnant of porous, vuggy quartz along the thrust with enhanced plumbing. So if any later hydrothermal circulation takes place, the thrusting did the groundwork to allow for that to circulate and be focused on the thrust. So the mineralization is likely very much younger than the thrust, but the thrusting and the aplites did some of the work to make favorable plumbing to get the minerals in there. So regional thrusting is widespread in Keno District. We're bringing back McTaggart's model. So, you know, he said it first. I think he was right. Epithermal mineralization is much more widespread than previously recognized, and it's occurring in both the east and the west ends of the district. And we used to, including myself, think it was largely just a West End feature, but we're finding it actually throughout the region. And the detailed, the fine quartz texture is quite mappable. Sometimes at surface, the sulfides get leached and weathered away, but the diagnostic quartz fabric remains, and we can map that. Thrust can also act as conduits for aplite intrusion. And you saw the example of that at Silver Basin and Caribou, and host later epithermal event. Soil anomalies in East Keno define broad targets for exploration across thrust structures. And the main phase faults are present out there as well. There's geophysical trends which we think we can pin to that, and exploration work is ongoing over there. So thanks for your attention. That's basically what we had to say for today.
Thanks very much, Greg. That was really interesting. Our third speaker this morning is Rob Duncan, VP of Exploration with Alianza Minerals, and his talk is entitled "Shining a Light on Mount Haldane's Hidden Silver Veins."
Thanks, Carolyn. I'm really excited to be here today virtually, and wanted to give a big shout out to the organizers for the pivot that they undertook to make this conference still happen and let us all share information today. So thanks to all of those folks. I'm excited to be able to talk to you about our Haldane Silver project up in the Keno Hill Mining District. I will be making some forward-looking statements, and I certainly hope that some of them come true in the future. So jumping right into it, where is Haldane? Haldane's on the west end of the Keno Hill Mining District, of course, an extremely important silver producing district, Canada's second largest. And one of the things that really sets it apart is that high average production grade, over 1,100 grams per ton silver. Alexco's done a great job in the core of the district, growing reserves, resources, and getting back into production. Haldane itself is 25 kilometers west of the main part of the district and 30 kilometers north of Mayo, located in the traditional territory of the Natchitoches Dun First Nation. Switching over to a Google Earth image, we have road access into the project. There's road trail access right to the backside of the mountain itself, where the silver occurrences are located. It has seen historic past production right in the discovery days, 25 tons of over 3,100 grams per ton silver. And then more recently, of course, our own success in surface exploration drilling, where last year we had a 1.2 meter true width intersection of over 3,200 grams per ton silver. I hope to be able to demonstrate to you today that it's still extremely underexplored, and that all the structures and vein fault mineralization that we see today can be expanded to depth and along strike. And part of this is sharing the couple of discoveries that we've had at Bighorn in 2019, and as well as the West Fault. We think there's great potential to grow the system, and we have a 10-year Class 3 land use permit in place to help us carry out all that work. Switching just to a scenic shot, an overview shot. This is taken from heart of the district at Hector Calumet, and you're looking over to the west to Mount Haldane itself. Much of what's in front of you is the key unit, the basal quartzite unit of the Keno Hill quartzite formation. And Haldane sticks up as this mountain. And I think an important point to raise is probably the upper 60% of it was not glaciated in the last glaciation event. So in terms of talus and regolith and oxidation profiles, they're quite extensive, and makes it a little more challenging in terms of prospecting out recessive fault vein occurrences. Very brief word on the geology, and Greg's done a great job in this, and there's many other experts. The key pieces that I'd like you to focus on is that basal quartzite member of the Keno Hill quartzite formation. Vast majority of occurrences and past production coming out of that unit, and the same is true of Haldane. All or the vast majority of our silver occurrences are also in that unit. And then above that, the sourdough member, and Greg's raised the intriguing possibility that some of that at least is Ern group. We've recognized that at Haldane. That came from mapping efforts by Murray Jones in 2018. And as a consequence, sort of the interpreted location of the Robert Service Thrust has moved south in the vicinity of Haldane. Other key feature being located on the south limb of the McQuestion Antiform. We're going to take a look at a photograph down northwest down the Bighorn Creek Valley now. And so this is what things look like. This is Bighorn Creek itself, South McQuestion River in the background, and the access road into the Eagle Mine. We're going to be focused on this flank of the mountain here in an area we call the Mount Haldane vein system, and specifically the West Fault area where we've been having our drilling success. And if I have time, we'll touch on the Middle Cough, which is over the Bighorn Creek Fault and is where the majority of the past production came from, as well as down here in the flank to the northwest at Bighorn, where we drilled a hole in 2019 with some success. In terms of the exploration history, the original discoveries at Haldane were right at during and on the tail end of the original Keno Hill discoveries themselves. And that's when the majority of that underground production occurred. And then there's decades where there's no recorded work, all the way up until the mid-60s when Dr. Arroejo, Silver Titan, went in and did some more underground work at Middlecoff and Johnson and some trenching as well. And then beyond that, only some sporadic work on the tin, tungsten, and gold side of things, right up until when Equity Exploration acquired the project in the early 2000s. Alianza took the project on in 2018, conducted property-wide soil sampling, prospecting, mapping to try and prioritize drill targets. And since then, we've drilled 14 drill holes. So despite 100 years of exploration here, there's a grand total of 27 surface exploration drill holes on the project, and it remains very underexplored. So focusing down on what we're going to be talking about today, this is this Mount Haldane vein system area. There's a series of parallel, subparallel, north-northeast striking fault structures with vein mineralization within them. You have the Johnson, the main and the main south, and then the West Fault itself. What this looks like from a photograph from Middlecoff over is, alpine, subalpine. This is all basal quartzite unit of the Keno Hill quartzite formation, very blocky talus, obscures the structures themselves. Despite that, you can see oxidized manganiferous brecciated silver mineralization at the main and the main south. This recessive area here is the surface expression of the West Fault. There's some weak soil anomalies in a trench at the very top of the hill here, and otherwise not a great surface expression on the structure itself in terms of mineralization. So the original drill hole in 2011 was actually targeting the main structure. And so in many respects, the silver mineralization here was a blind discovery. So going through in detail, what I would like to do is sort of take you section by section through the West Fault itself. We'll start off at the southwest and move to the northeast. As I said, it was discovered in 2011, and that original hole had a true width of 3.36 meters of 108 grams per ton silver. We like the strength of the structure there, and of course, it's the right mineral assemblage present, and wanted to test a long strike and down dip to the southwest of that. And that's what we did in 2020. And this hole 19 was a bit of a game changer for us. Very strong wide structure within that, 8.72 meters true width at 311 grams per ton silver. So in 2021, we had a view to systematically doing 50-meter step outs down dip and along strike. That program was successful in adding over 100 meters of strike length and 90 meters of dip direction with silver mineralization, and that remains open in all directions. And the highlight result being from hole 21-24. True widths again, 3.14 meters of 1,351 grams per ton silver, with a core of high-grade vein intersection within that of 1.26 meters of over 3,200 grams per ton silver. So looking at the first section, this is a section with hole 24 on it. We have basically two structural splays, one located on sort of on the footwall side, and then a second one higher up. And mineralization can occur along both. So we basically have two splays of mineralization developing. This lower one we call WF1 and the upper one WF2, and you'll see that in a moment. Overall, the strength of each splay structure can be 8 to 10 meters wide, and then it can be separated by up to 10 meters. So overall, the West Fault vein complex itself is 25 to 30 meters wide. It consists of classic Keno Hill assemblage. It's manganiferous siderite, carbonate vein material with galena and sphalerite, and again, those inclusions of tetrahedrite within the galena. And in some cases, we've seen a couple of native silver wires. So what does the structure look like itself? You're seeing a photograph of the entire West Fault structure in hole 24 between the green arrows here and here. You can see a number of brecciated and gouge zones developed in quartzite and also in phyllite units within that quartzite. And then the silver mineralization picks up between the red arrows where we have an increased abundance of the siderite material and galena and sphalerite appearing. And that's that 3.14 meter intersection that returned over 1,000 grams per ton silver. The massive siderite, galena, sphalerite part of the vein is between the pink arrows, and you can see it's been brecciated and has healed itself, and that's where the 1.26 meters of over 3,200 grams per ton silver comes from. You can also see a bit of a damage zone and horsetailing of siderite on the footwall side of the structure as well. Couple of quick close-ups on this. You've seen this one before. You can clearly see the siderite here, fine-grained galena, and the sphalerite. That fine-grained, poorly developed cleavage in the galena can often indicate you're going to get higher grade silver, and both these samples were over 3,000 grams per ton. Zooming in one more stage, again, you can see the paragenetic sequence here. Siderite and then sphalerite and galena is last in line, and the two circles are just focused in on these two occurrences of native silver wires within the intersection. Moving on to the next section, here we're going to focus on hole 21-25, but you can see the development of WF2 and WF1. So the structure is through going, you can see it clearly here, but in hole 25, WF1 is simply about half a meter of a gouge zone, crush zone. So I think when you're logging, it's really important to pay particular attention to these things. They might not look like anything, but you could be 50 meters away from a significant silver intersection. Again, siderite, it's been brecciated and healed. This green mineral assemblage here is largely chlorite with a couple of clays, and that's light brecciation and healing. The vein mineralization itself, you can see open space texture and infilling. You have two generations of carbonate deposition. They're the same composition, but the first is without sulfide. The second one, there is galena and sphalerite in it, and then the sulfide infilling at the last stage, the sphalerite and galena. Overall, the structure is striking about 210 to 215, and dips a bit variable, but in a reasonably tight range between 61 and 70 degrees off to the northwest. Third section, the farthest to the northeast, a little bit different. This is hole 27. Again, the intersection is up in WF2. The structure in WF1 is still there. A good wide structure again, silver mineralization down at around 81 grams per ton silver. What I think is important here is the nature of the siderite. Again, banded open space type filling textures, as well as some sphalerite and galena, but we're also high enough in the system here to be in the transition zone with the oxidation profile. And so you can see the oxidation. I don't think this was ever as high a grade intersection as some of our others, but there is a possibility of leaching out of silver and base metals. So putting this together in trying to determine what we're looking at, you're looking at an incline long section down on the face of the structure itself. We're looking down to the southeast, and we've done gram per ton meters of silver equivalent, so total metal endowment and thickness. And everywhere that it's a circle, it's on the lower WF1, and the hexagons are WF2. And this line is more or less in and around the area where we see the crossover from mineralized portions of WF1 to WF2. That line has a 60-degree plunge in the plane of the vein and sort of corroborates our earlier ideas where we favored a southwest plunge, possible plunge orientation to mineralization. You can see the highest grade intersections are on that southwest side, and possibly in and around where the step over actually occurs. The other feature is this potential for this vertical control, and whether that's a result of just where the oxidation profile is, or perhaps more of a stratigraphic control. Things will be more or less dipping at us at about 20 to 30 degrees in creating open space in a jog. I'm not certain. So I was thinking about the overall architecture and thinking about trying to draw an elaborate structural block model here. And I think, I'm going to fail at that. So I was looking at this beam of wood instead, and it's holding up the roof of a cabin. So the roof's over here and the floor is over here. So it's in pure compression. And this wood's responded and opened up an extension in this direction. I think this is very similar to what we're seeing in terms of architecture at the West Fault. Obviously, we didn't see pure compression, but some form of compression with shear and probable dip slip movement. But the rocks have responded in a very similar way. So my long section is right in this area here. So the structures are through going, they overlap, and then they have areas where they're open up the most. And we're always looking for that link between the micro and macro scale. And so it's quite possible that perhaps we have another WF3, and that the whole Mount Haldane vein system sort of mimics this architecture, and you're actually going from Johnson and stepping over to Maine, and then again stepping over to the West Fault. So in terms of what we're going to be doing in this year, in 2022, we're going to remain focused on the West Fault. We favor this southwest orientation for possible plunge and controls on the high grade silver mineralization. So we want to follow up mostly over here. But if you're going to be completely unbiased by this, you really shouldn't ignore the intersection in hole 25 and whether the upper WF2 might also develop out in this region. So moving on to a couple of other examples where we've sort of put together our learning over the last couple of years. The first being Middlecoff. And so this is over the Bighorn Creek fault. It's a vein that runs more or less north-south and dips to the west. And that's where that high grade underground production came from. 27 tons of over 3,100 grams per ton silver. Also underground sampling by AHO returned 775 grams per ton over 13.7 meters, as well as this high grade underground drill hole interception at 1.2 meters of 2,700 grams per ton silver. We had some success in 2019 and 2020, and it's all leading us to that similar idea, that potential for a southwest plunge. And we would like to get back and drill test Middlecoff in this area underneath this underground drill hole that has never been followed up. In terms of sort of earlier exploration, I mentioned in 2018 that Alianza conducted property-wide soil sampling, mapping, and prospecting. And that focused on the basal quartzite unit. Turned up a number of anomalies, one of them being the Bighorn, which we ended up drill testing. That Bighorn soil anomaly is 150 meters wide by 900 meters, and it's got hundreds to thousands of ppm lead in soil with very strong silver numbers supporting that, including this particular one, which was almost 64 grams per ton. There's a number of deformation zones and structures trending more or less north-south that you can see at surface. We're in the basal quartzite unit, and we see brecciation at surface as well. So we put one hole through that, hole 1915, and it was a great success. It returned 4 different structural intersects. The degree of oxidation was much shallower, and the best result was in this number 1 here, 2.35 meters of 125 grams per ton silver. Maybe a little more silicification around than some of the other vein occurrences, but the siderite, galena sphalerite mineral assemblage is there. And I think the key to focus on here is that intersection, number 1, is almost identical to the 2011 drill hole at the West Fault. So what's important is strength of structure and the correct mineral assemblage. And you know, very often, if you have that, you might have potential for productive silver mineralization close by. And in the case of the West Fault, we were actually less than 50 meters away. So that wraps up the talk. I hope I've been able to demonstrate to you that Haldane is definitely part of the Keno Hill district, and the mineralization there is similar, if not near identical, to the main deposits at Keno Hill. We have 2 areas for expansion, excellent areas for silver mineral expansion, that being the West Fault Middlecoff, as well as potential for new discoveries even after 100 years, as demonstrated by the Bighorn, with only 1 drill hole in it within a very large soil anomaly. So as I said, our plans for this year, get back in the field and follow up on that drill success at the West Fault. That would be our focus, but we're desperately eager to get back to Bighorn and the Middlecoff as well, to be able to put more tests in those 2. So thanks everyone for your attention, and happy to answer any questions in the Q&A.
Awesome, thank you, Rob. So that concludes our talks for the Beaver River / Keno area this morning. We do have a couple of questions that have come up. I'm just going to scroll back and pull the first one that came in, and it's for you, Greg. And it's from David Moynihan, and it's sort of a multiple question, but he's asking about the relationship between your thrust faults, the aplite bound thrust faults, in the North Virgin direction relative to the northwest deformation described by Murphy, the Tombstone Strain Zone. Do they overprint Tombstone Strain Zone, and what do you think is the timing relationship between the Roberts Service thrust and the Tombstone Strain Zone? So you can unpack those one at a time. I think you can see them in the chat, I hope.
Yeah, so there is a overprinting phase of deformation and folding, and actually on my introductory slide, which was just the title and so on, I actually had a field shot of that late overprint, and it's it plunges the fold axis plunge gently to the southeast, and they're largely open folds. The so-called Mayo Lake anticline, which is a broad regional structure that Cairn mapped in the 1940s, and it still holds true. And so there is a later, so it postdates the schistosity. It has a upright spaced cleavage locally. It's not particularly intense. It's there and it's real. It has a stress compression direction to the northeast that is consistent with the main fault stage in a sinistral sense. So the mineralized faults such as Keno Hill and the Hector, which I displayed, if those are sinistral faults, they relate in their compressive direction to the, there's also associated folding, weak and open. And it's sort of an add-on to the discussion. With 20 minutes, I didn't have time to get into that. Its effect is lesser on the map pattern, but when you see these thrusts and they're winding their way around the countryside, partly because they're shallow dipping into gulches and so on, but there is also an overprint folding imposed on top of the trace of the thrust faults. So I don't know if that's the same one that other people were talking about, but there is a late stage on there, but it's nowhere near as intense as the schistosity related thrusting that I was talking about. The Tombstone thrust would seem to be the uppermost map thrust, so like the roof thrust or the hanging wall thrust to the Imbricate stacking or thickening of the Keno Hill quartzite. So it seems to be part of the same family as the thrust I was talking about, and that would predate the upright open folding that I'd mentioned. So not to say that's not important. I mean, I think if you really want to synthesize the compression, I showed it in the StereoNet map, right? I was explaining that the main stage faults are cross-cutting and post-dating the aplites and the thrusting, and that there's also a folding expression of that event. So to me, it appears potentially the 94 million years old is potentially the same or a similar age to the thrusting. So the aplites need the thrusts to intrude, but there are small truncations that you see as well. So I mean, they might be so-called synkinematic is the terminology they might use. But the thrusting then might be 94 million years old or a bit older. The aplites come in at 94. There's some argon dates around like 89 and quite a bit younger, which would be the strike slip upright galena veins and that open folding that maybe you're referring to. And then following that, I mean, some of the argon dates, and they're on Alexco's excellent map, basically document things as young as 68, which would be a McQuestion age. And all I know is textually the epithermal event is younger. How much younger? I mean, it could follow immediately as part of the continuum paragenesis of the galena veins, or in fact, it could be absolutely much younger because it truly is a shallow, and the amount of erosion needed to get the region to a shallow setting, there could be, decades of tens of millions of years between the events. And like I said, the quartz in the main phase, these are deep, high pressure quartz, which boil off. I did a bunch of work on the metamorphic oriole, and it's like 3.5 kilobars, which is 10 kilometers depth for the aplites. Right, and that's again a whole other talk, but that's getting into the mesothermal realm, and the epithermal is certainly shallower than that. In which case, potentially a big time gap between the two. So I don't have an absolute answer for that. I'm just speaking in relative terms. But epithermal, epi means shallow, and it's a different setting. So a lot of the plumbing, though, was established early on, which was the case I was trying to make. We sit in hot springs here in the Rocky Mountains with hydrothermal systems coursing through these thrust faults that are 70 million years old. So the hydrothermal system, it's active with sulfur and everything else, is 70 million years younger than the actual thrusts they're using. That's a bit of an analog to hydrothermal circulation on Rocky Mountain thrusts. Yeah, I had a cute little picture in my talk. I mean, I had to shorten it back, and my co-authors helped me pare back all kinds of stuff. Like anyone here, I mean, we can talk for a long time because these things are so complex and interesting. I don't know if that answers the question, but there is northeast southwest compression. The regional expression of that is the Mayo-like antiform that overprints the aplites and the thrusts. Well, actually, the timing is potentially quite close. It's really hard to unravel the exact timing of that. I'll just say it overprints the schistosity, the main penetrator schistosity, and maybe consistent with strike slip faulting on the limb of that, which is the strip of Keno Hill quartzite running through Galena and Keno Hills.
Okay, thanks. I think in that answer, you also answered there was a second question about the age dates, specifically the Roops Lake Pluton. And you showed some ages to the north and to the west of there. And it was, I think the question was to confirm whether those are aplite dike ages.
Yeah, so hopefully let's make that clear, very clear, that I hope I'd mentioned during the talk, those are all igneous age dates from zircon, and the samples I showed were from aplites. Then I went into the talk about the segment of the aplites. And on Keno Hill, we have a 94 plus or minus 1.6 million years, which is, you know, a bit of an error bar there for sure, but it really puts you squarely into the Tombstone age of ages, and that's consistent with other aplites. We just didn't know if the aplites maybe were bimodal and maybe showing a McQuestion component or something like that, right? Because I'm talking about some of this younger epithermal stuff, and it came out as Tombstone age. So either the thrust structure was sitting there passively, being an older structure, and it delaminated when the aplates forced their way in. But the aplates, they still need a regime where, you know, the minimum compression is vertical, right? You're lifting that rock up, you're delaminating in a horizontal direction. And this is why I think that stress field that it needs is not unlike the stress field for the thrusting. So I think you can use that as a generalization, not a proof or determination, but a generalization that maybe the aplite and the thrusting are, you know, overlapping somewhat in their timing.
Okay, awesome. Feel free to post more questions. I did have a question for Tyler, just sort of arm wavy question. You showed that photo of it went from the base of Gillespie up through Pinguicula through to Hematite Creek, a huge thick section of carbonates. They all sit on the southeastern edge of the Yukon stable block, so it's obviously a long-lived structure. Does the shelf slope break in there play a role in as a conduit for mineralization in the region? Even though, I mean, your mineralization events are all spread over quite a long time range as well. Oh, you're muted, I think. Still can't hear you. Huh, that's weird. Anybody else having trouble hearing?
Yeah, I can't hear Tyler.
Or no one else hear him? Okay. Not sure what to say, Tyler. There we go. Still can't hear. Maybe we're just not meant to know what the significance of that structure is. Tyler, you can type the answer in the chat if you've got some thoughts on it. Maybe in the meantime, Rob, just a question. The map you showed with the West Fault structure, the geology in the background had primarily Keno Hill quartzite with, I assume, sills of diorite that were folded with a northwest general axial trace on the map. And you mentioned that you had southwest plunging, the highest grade mineralization plunged southwest along the surface of the northwest dipping faults. Is that plunge parallel to the fold plunge in the area? Are they related at all?
They could be, and in terms of that sort of detail, I think we just don't know enough at the moment.
Okay.
Of course, you know, that particular map on the slide's a gross simplification of it, and you know, drill hole to drill hole, we really tried to focus on some stratigraphic correlations. And in detail, you know, we're talking about 10 to 20 meter thicknesses of pure quartzite and then pholitic layers in between. One thing that could be quite important is sort of just above all of those west fault drill holes, maybe 20, 30 meters above it, are one of these dioritic sills. And so whether that's a trigger in itself for getting the structures to open, as well as the quartzite beneath it, I'm not entirely sure. But to try and answer your question, it's entirely possible that that's the case.
Yeah. Okay, awesome. Tyler, do you want to try talking and see if we can hear you now?
Yeah, I can't imagine. Do you hear me now?
Yes, yeah, perfect.
Yeah, I don't know why my microphone crashed or something. Yeah, so what I was going to say is, you asked about the correlation or the relationship between the margin of the Yukon stable block and that transition from the platform, the thick lithosphere, to the thin lithosphere in the Selwyn Basin, and then the relationship to mineralization. So yeah, I think there's, you know, the Dawson fault and possibly the Kathleen Lakes fault are these very long-lived structures. So they've existed since at least the Precambrian, I think, the Neo-Proterozoic. And so they've been reactivated as thrusts, as a strike slip. And so yeah, there's these long-lived pathways for fluids, and I think that's reflected in the timing of mineralization. You have timing associated with this corridor spanning from the, you know, Precambrian up to more recent, and I think also another thing to attest to them being a fluid or mineralization conduit is the different types of mineralization. Like there's a huge variety in the style and the metals that you get associated with that transition. So yeah, I think you just have the Yukon stable blocks, this big, thick lithosphere, and things are butting up against it, you know, and as you come south, the regular lithosphere, and it's yeah, it's conducive for mineralization.
Okay. Good. Any other questions from folks? I'm just scrolling up to see if I missed any. Another one maybe for Greg, given the spatial association of the aplite dikes along the thrust faults, as you say, it's sort of a chicken and egg thing. Maybe the imbrication created the dilatancy that allowed those sills to intrude. Do they have any kind of geophysical signature that you could use to map their extent? Like you showed them a series of sills to the north of where you've been working in areas where there's not much outcrop exposure. Could they be, do they have a magnetic or any kind of signature that you could pick up to trace them even further westward through Alexco, even down to Mount Haldane?
Well, the thing there, so they're approximately say, you know, I think the thickest one we saw was maybe 10 meters thick. So they tend to be 10 meters thick, sometimes a bit thinner than that. So, you know, at a geophysical scale, at least from, you know, the broader kind of regional set of data, I'd have to say, I can't say that we are able to map them in terms of the aplites being responsible for geophysical signature. The thicker packages of rock and underlying and overlying are probably controlling more of the geophysics. And of course, you have adjacent and within the package, these much thicker and possibly magnetic diorite sills from the Triassic, right? and they would basically end up influencing broad scale geophysics more strongly than the aplite. So basically that would be my long-winded version of no. But that's also maybe a scaling issue if you had you know, something on the ground with detailed grids of geophysics. You could then potentially follow up and try and map these things around. And depending on the outcrop, you know, the aplites might pinch away, but you're still establishing the contact through the thicker packages of quartzite below and urn group above. You know, I think the scale of geophysics is seeing those contacts more. Some of the contacts and the map I used, I mean, in one summer, we covered a fair bit of ground, but I mean, there's still all kinds of gaps that need to be filled. And so we did, of course, use geophysics to help draw some of the lines between either quaternary cover or not, of course. So geophysics did play into how we ended up drawing these. And we used the established packages at Keno Hill from the detailed work of Alexco and detailed work of Boyle and going back into the years, of course. So those are very useful to help us. And we have the same stratigraphic breakdown, and we're mapping it on a more detailed and continuous basis to the east of where other recent mapping stopped. So yeah, geophysics is important as always. It's just take all the data and put it together and use it as best you can in an integrated way, which is why these GIS packages, which I spent a lot of time on YouTube learning all the bells and whistles. There's no end of tutorials on there, and I think I read every one of them. So we can overlay these layers, of course, and play that game. So there's some really strong tools for us out there right now. And the YGS data too is great. I mean, downloaded all kinds of stuff, and so that's been super useful. Your 2020 airborne geophysics of the region that we downloaded has been super helpful. The large, I have to say, I mean, so the Tombstone suite, though, the large plutons on Aeromag stand out like a sore thumb, and that's another slide I had. And amazingly, so the metamorphic aureole to those has a pyrrhotite component. So it's pyrrhotite and biotite. And the pyrrhotite is, of course, a magnetic mineral. And so the metamorphic aureoles stand out more strongly than the actual granite. So the granite in itself is anomalous, but the pyrrhotite in the host rock surrounding that pushes the Aeromag to an even higher level. So you end up with a big donut. And these could be, you know, 1 kilometer or 2 kilometers around some of these plutons. We've also, I mean, we've ground truthed, and I've worked in the past on the metamorphic aureole around the Root Lakes Pluton. And it has, you know, big porphyroblast overprinting the schistosity. And a key mineral is storolite. I mean, I'm getting into the petrology of metamorphism here, but that's a pressure sensitive mineral. And I bring it up just because that's the one that's telling the depth is greater than 3 kilobars for that Pluton. And 3 kilobars in depth conversion is something on the order of 10 kilometers or more depth. So the Tombstone suite at this end of the district was coming into a crust at mid to lower crustal mesothermal kind of levels at 10 kilometers, pretty deep. And the Keno veins probably follow close on the heels of that. Maybe they're somewhat shallower, but maybe not too much shallower than that. There's a YEG paper on the metamorphism that I put in the YEG like in 2009 if people are interested in depth of Pluton emplacement.
Okay, that'd be awesome. Just speaking of the regional geology, I should mention that Maurice Colpron is updating the bedrock geology compilation to incorporate some of the recent mapping that YGS folks have done, and Al McConey's map that Greg mentioned on the Alexco property. So that's due to be re-released shortly. I'm not sure if we're aiming for a roundup or shortly after that. I guess it's done when it's done. But Mo's written a YIG paper just describing the spatial database and the layers and so on. So that'll be available soon too. And while I'm plugging YGS, I'll mention we recently released a permafrost database for the territory. And it might not be something that would jump to top of mind of interest for you, but it includes all the publicly available borehole data with information on logs and superficial materials and ground temperature data where they exist. So if you're looking at infrastructure builds or anything and need to know about slope stability or how fragile the permafrost might be in your area, that's something you might want to have a look at. And I also mention it because there are quite a few gaps in the data. And if you have boreholes on your property that you'd be willing to have us come up and drop a thermistor string down your hole, we'd be happy to do that. It's Jeff Bond's group who's the lead on that, Derek Cronmiller. And if you don't know Derek, you can just email geology@yukon.ca and we can connect you. They'll be looking to get out to some field areas next summer and fill in some of the regions where we don't know much about ground temperature or permafrost thickness or character. So it'd be really helpful to get access to your properties. Mo has chatted here, the new GIS data and map revised legend should be ready for roundup. So if that's the case, we'll have it, you'll be able to download it from the Yukon virtual booth. And if you don't get it there, it'll be on our website. Anyway, I'm not seeing a lot of further questions. I don't want to drag this out just for the sake of dragging it out. So maybe I'll just mention the upcoming sessions. There's 4 more sessions in this Geoscience speaker series. Next Tuesday is going to focus on critical minerals. And then the following Thursday, the 20th, the session is focused on the Dawson Range copper porphyry belt. There's a lot of talks in that session. It's going to be a good one. And then the following Tuesday morning will be gold projects in Yukon. And then the last session is a bit different. It's not so much technical talks. There's 3, it's called a partnership session. There's 3 presentations. One is a panel discussion on some of the work to streamline regulatory process. One is a talk on health and safety, evolving protocols given COVID and other things, other challenges. And then it's going to end with Laura Lee Johnstone, the president of the Chamber of Mines, and Minister Ranj Pillay, who's the Minister for Economic Development. And they're having a chat on how to advance mining and exploration in Yukon. So they're all free. I don't know if everyone's registered for them, but have a look at the website and that's where you sign up. Okay, barring any last questions, I think we can call that the end of the session. Brianne's just going to come on and say a final few words to wrap up. And thank you all for participating. It's been great. And thanks to our speakers. They were a very interesting suite of talks.
Yeah, thanks, Rob and Tyler. Great clarity there. Thanks.
Okay, hi, Brianne.
Hi. Again, thank you everyone for joining us, and we look forward to seeing you again at our future sessions. I just wanted to do another plug and thank you to our now silver sponsors, Metallic Group of Companies, SGS, Smalls Expediting, Northwest Tile Tetra Tech, Sodexo, Whitehorse Gold Corp, and again, our partner YGS, Yukon Government, and BMC Minerals. Really appreciate everyone's time today. Thank you very much. The talks were great.